I'm very happy today to introduce Dr. Yu. So she's currently a Phillips Griffith Assistant Research Professor in the Department of Mathematics at Duke University. She got her PhD in mathematics from RPI in 2023. Her advisor there was Ranji Lei. Her research interest is mainly in applied and computational mathematics, with current focus on numerical methods and applications of optimal transport and mean field games. We're going to talk with today about computational mean field games from conventional methods to deep generative models.
Thank you, Professor Kundo, for the introduction and invitation, and I'm happy to be here to overview the point. So today I'm going to talk about some computational methods for mean field games, and the first part I will talk about some conventional methods in low dimension Euclidean space, and then we switch to neural network, and I will talk about some relation between mean field games and generative neural networks in the second part. So to start with, let's talk about why we care about mean field games and what's the background about mean field games. So there are many problems. You want to study the flow of some density distributions. For example, the problem of optimal transport actually wants to find a way you move one flow to another flow. You want to move one density distribution to another density distribution with the least effort. And there are also some cases you not only care about the dynamic cost when moving the density. There is also some other cost, interaction cost. For example, if there are more people gathering in one location, then it may take you extra effort to go through that region. And there are also cases you are solving the density distribution flow on a manifold instead of on regular Euclidean space. There are also cases you want to study the flow of two different groups. They are also related. All these kind of problems, they are related to density flow. And recently, in machine learning and deep learning community, they study generative network. They study the generative model. The key idea on generative model is you start from a simple distribution, and step by step you evolve your simple distribution to the data distribution you care about. This generative model can also be viewed as a problem study how to move one density distribution to another density distribution. So mean field game is one way to model the density evolution. Essentially, mean field game cares about the density distribution and decision making of infinitely many players in a non-cooperative game. So suppose now we have a game and there are infinitely many players. What's the goal for each of the players? So the goal of each of the players is to find if at time t the player is at position x, then its goal is to find a velocity or a control to guide its following trajectory. And he wants this following trajectory to minimize some cost. Usually this cost consists of three parts. One is the dynamic cost, the second part is the interaction cost, and the third part is the terminal cost. Dynamic cost usually tells you how much effort you need to pay to move from this position to the other position. And interaction cost is usually tells you you interact with all the other players, what's the cost by doing this. And terminal cost is usually the cost at the terminal position. So for every single player, they are trying to solve an optimal control problem. And by solving this optimal control problem, this will give us a Hamilton-Jacobi-Bellman equation. This is on the individual level. On the other level, if all the players, they take the same strategy, then you can also try to model you can use this strategy to model the density of all the players. And this will give us the Fokker-Planck equation. So now the problem is Hamilton-Jacobi-Bellman and Fokker-Planck, they are all some very famous equations. What's something new in mean-field games? Why people care about this game? So let's take a closer look at this problem. Let's take a look at an example. Suppose so we should pay attention to this interaction cost and terminal cost. These two costs actually tells you your cost depends on what other players they are doing. So this density is the density distribution of all the other players, is the mean field term in the cost. If all the other players act as this, you may get one optimal control. And if all the other players act as another way, you may get another optimal control. So here you see this value function of the Hamilton-Jacobi-Bellman equation depends on the density evolution of all the other players. On the other level, that means your optimal control depends on the density of all the other players. But at the same time, the distribution rho also depends on B. So you give me an optimal control. Everyone follow the control to move their trajectory, and then they give you a density evolution. So something that is very important in mean-field game is your Hamilton-Jacobi-Bellman equation and your Fokker-Planck equation. They are coupled together. You get a density rho, you will get a phi, and your phi will on the other direction change your density rho. So now the question is, which one is you care about? Do you want to solve the Hamilton-Jacobi equation, or do you want to solve the Fokker-Planck equation in mean-field game? And the answer is we want to solve both at the same time. So this is the very important concept in mean-field game. We want to find the mean-field Nash equilibrium. This is a special pair of the control and the density. On this special pair, you will see the value function phi is the optimal with respect to the density rho. And at the same time, the optimal control induced by this phi will give you exactly the density rho. So that means if the players, they don't change their trajectory, they don't change their control at the same time, then they will not change the rho and phi. This is the equilibrium point. So based on what we talk about, the PDE formulation of the mean-field Nash equilibrium is very straightforward. You just combine the two equations, PDEs together, and you get the PDE formulation of a mean-field Nash equilibrium. But let's take a look at this system. It is not very simple to solve. First, in the Hamilton-Jacobi equation, you have this nonlinear curve, and it depends on the density rho. This Hamilton-Jacobi equation is moving backward in time, which means you have the your time boundary condition is on the terminal. And you look at this Fokker-Planck equation. The Fokker-Planck is linear, that's fine. But if you look at the Fokker-Planck equation, it's moving forward in time. So you cannot do something like forward Euler or backward Euler to solve this system, because one of the equation is moving backward and the other is moving forward. That's the difficulty of this PDE to solve this PDE formulation. But a good thing is when the problem has some nice structure, then we can formulate this PDE problem as the optimality condition of an optimization problem. So here is the condition. If the interaction cost and terminal cost, they have some potential, then this PDE system can be written as the optimality condition of an optimization problem. And to make this optimization problem easy to solve, instead of solving with respect to rho and v, we write M as the product of rho and v and formulate the problem in this way. So you may ask, what's the good thing about this formulation and the optimization formula? So let's first take a look at this constraint. Although it's the PDE constraint, if you take a close look at it, it's linear in terms of rho and M. So we have an optimization problem with linear constraint. That's a very nice property. We have many different first order methods to solve this kind of problem. And the better thing is, usually this objective is convex in terms of rho and M. So now I have an optimization problem. The objective is convex. The constraint is linear. You cannot find a simpler constraint optimization problem than this. So to take a closer look at these two formulations, maybe let's see why they are related. You first write down the variational formulation and write down the Lagrangian function of this optimization problem. Then you can derive the first order optimality condition. The first equation eventually will give you the Hamilton-Jacobi equation. The second equation will tell you the optimal control, and the third equation is just a continuity equation, just the constraint. So that's how these two formulations, they are related. So now we talk about the motivation of mean field gain, the background of mean field gain, and we see two formulas of mean field gain. Still, it may not be clear why people are interested in mean field gain nowadays. So here are some examples that are some concepts that are very popular in machine learning and also in traditional applied math community. And they are all related to mean field gain. So the first concept is called optimal transport. As many people know optimal transport, it's this optimal transport induce a metric on the probability density space. And the Van-der-Moog-Grenier formulation of optimal transport can be viewed as a special case of mean field gain. It's just that you don't have the interaction cost, and the terminal cost is a hard constraint. Sorry. And recently, this Wasserstein gradient flow is also very popular for people to doing samplings. And it can also be viewed as a special case of mean field gain. You weight this dynamic cost by 1/h, where h is your step size in the Wasserstein gradient flow. And the terminal cost is some functional on the density that you want to minimize. So these two, they are related to mean field gains. But mean field gains, it has the interaction cost, which makes it more versatile to deal with a more general class of problems. And another thing that is popular today is called generative model. You basically want to start from one distribution to another, to a data distribution. And recently there is a paper study the relation between generative models, some popular generative models, and by giving them an interpretation by mean-field game. So in their paper, essentially most of the generative models can be viewed as a kind of mean-field game, but with different dynamic costs, interaction costs, and terminal costs. So based on that, you can choose your favorite dynamic cost, interaction cost, and terminal cost, or based on your application, and you can also design a new generative model. And we will see how they are related in the second part of our talk. So for the rest of the time, I will first talk about some conventional methods to solve this mean-field game system. And I will also talk about how do we use neural network to solve it in high dimension, and how this method can help us to improve the training of the neural network. So the first part is a joint work with my PhD advisor, Jiajia Yu, and Wu Chen Li and Professor Stanley Ocean. So let's recall the two formulations of mean-field games. We mentioned that the PDE formulation, it has the nonlinearity, it has the forward-backward structure, it is not easy to solve. So, and the variational formulation, it has a convex objective, it has a linear constraint. So what we do is based on this variational formulation and design and apply some optimization algorithm to solve it efficiently. So let's make our location concise. We just write all these things as the calligraphic L of rho and M is a convex term in terms of rho and M. And write this operator A as the constraint. It's a linear operator. So now we want to solve this problem. What we do is very simple. We just do gradient descent with respect to the differentiable part, and do the projection with respect to the constraint. So you see this gradient descent is very simple. As long as I can compute this variation, I can get the gradient, I can compute this gradient step. And the next step is to do the projection. This projection is independent of the objective form of the objective function. So no matter how complicated this L is, this part, the complexity of this projection remains the same. The next question is this projection easy to solve? So let's see, what's the projection? What's the key part of computing this projection? The same thing we do, we first write the projection and write its Lagrangian formula and derive its first order optimality condition. So by computing the first optimality condition of this Lagrangian, we find that this is what we have. So as long as we can solve this Lagrangian multiplier phi, we can find the projection. And what do we know about this phi? So since this is the thing after projection, so it should satisfy the constraint. And by plugging this, the first equation into here, you will see phi actually, the Lagrangian multiplier needs to solve this equation. And what is AA adjoint? So we say A is the gradient operator, is the joint gradient operator in time and space. So A adjoint is just, A is the divergence operator, joint divergence operator. So A adjoint is just negative gradient, and AA adjoint is just Laplacian. So you want to solve this AA adjoint inverse problem is just to solve the Poisson equation. Now, on regular domains, we can solve this very efficiently with fast Fourier transform. So the projection can be very efficient. So this approach actually gives us a lot of flexibility to deal with mean field games with different objective functions. Because we mentioned the PDE is not easy to solve, and some other popular optimization methods, for example, augmented Lagrange and primal dual, they actually need to solve some sub-problem related to the objective function L here. So the problem is, if you just want to solve the optimal control problem, this step is very easy. You have the closed form solution. Every step you just need to solve a cubic equation. But if this L is very complicated, this sub-problem can be very complicated to solve, and you need to solve the optimization problem, solve another layer of optimization problem in your algorithm, and that's not very efficient. And for these two methods, the constraints usually imposed. The constraints are imposed implicitly. So if you do some early stop, you cannot get your solution that is close to your closely satisfy your continuity equation. And this sub-problem makes it difficult for you to do some perturbation analysis to see whether your discrete solution converges to the continuous optimizer as your mesh gets denser. But our methods can overcome all these problems. Our projection is very efficient. So this comparison is based on optimal transport, which is the best efficiency augmented Lagrange and proximal can achieve. And in this case, we still get a better efficiency and better efficiency comparing to their method. And we can further improve the efficiency of our algorithm by doing some multi-level or multi-grid strategy. And the good thing is we improve the efficiency without sacrifice our accuracy. And as I mentioned, we have the flexibility to deal with different objective functions. As long as you can compute the gradient, you can apply our algorithm to solve all these kind of problems. For example, you impose an interaction cost to encourage the individuals to avoid this white region, or you use some interaction cost to encourage them to concentrate in the region, or encourage them to separate with each other in the region. All this kind of thing, we can do it. And the even better thing is we can do some error analysis based on the mesh grid. So in this paper, in the paper, we actually prove that when your mesh size goes to 0, for each iteration, the discrete output converges to the continuous output on the mesh grid, and eventually your discrete output of the algorithm actually converges to the continuous optimizer on mesh grid. And here is the numerical results. We observe a more than first order convergence of the variables rho and m. and we observe a second order convergence of the objective function value. So that's the first part of solving mean field game on low dimensional Euclidean space. But there are many applications. You want to study the density evolution on manifolds instead of just on Euclidean space. For example, you want to study the source distribution on the Earth. This is kind of a problem on sphere. And there are also some irregular domains you want to study. And more popular in machine learning, people believe that the data sets, data distribution, all the data is located in a low dimensional manifold embedded in high dimensional space. So this motivates us to study mean field game on manifolds. We do some derivation, and the key point is we can have the same formula of mean field Nash equilibrium on manifold. The only thing that is different is this operator is now defined on the manifold instead of on the Euclidean space. And another nice thing is if this interaction cost and terminal cost, they have some potential, then we can also have the variational formulation of mean field Nash equilibrium on manifold. So if the manifold is compact connected smooth remaining manifold, then this variational form also preserve the same nice property as we have on Euclidean space. This constraint is linear and this objective is convex. So the next question is, how do we solve it on manifold? Still, if we take a look at the PDE formulation, besides the nonlinearity and the forward-backward structure, now you have a gradient operator on manifold. If you follow some extrinsic, for example, you try to do this by giving this manifold a local coordinate chart and solve it, push it back to Euclidean space and solve it on Euclidean space, you will make it very, very complicated because you add another layer of nonlinearity in the system. But if you follow an intrinsic discretization, you follow an intrinsic description of the manifold, you will still preserve the convexity of the variational formulation and the linearity of the constraint. So what we do is the numerical method and results currently can only apply to two-dimensional manifolds with triangular mesh. What we do is we get the triangular mesh and do a piecewise linear approximation of the function rho and do a piecewise constant approximation of the momentum m. And by doing this discretization, we can formulate the discrete problem, and it preserves the linearity of the constraint and the convexity of the objective. We also do the convergence analysis on Euclidean mesh. We see that when we increase the number of points on the mesh, the error actually decreases. And this method is it can be very flexible to deal with different manifolds. For example, we can deal with two-dimensional manifold embedded in high-dimensional space. This is an experiment for two-dimensional manifolds in five-dimensional space, and we rotate and get it back to three dimensions to draw this picture. And this is a genus 1 manifold. this is a genus 2 manifold, and this is the Mobius strip, which is a non-orientable manifold. All these manifolds we can deal with very nice, as long as you can give me a good triangular map of the manifold. And we can also deal with different objective functions. We can do some local objective, impose the sparsity of the density. We can do some global. Interaction. This impose the uniform. This informs the smoothness of the density. Okay, that's the first part. We talk about how to solve Mayfield games based on its variational formulation and optimization algorithms. But it's easy to see the limitation of this method because all the methods based on the mesh discretization of your space, and it's not realistic to do this in high-dimensional space. So now the problem is there are many applications you want to solve in high-dimensional space. For example, if you have so not only in high-dimensional space, even in low-dimensional space, you have multi-group densities that will increase the dimension of the variables in your optimization problem. And in high-dimensional space, for example, if you want to do some generative model that for images, the dimension can be very high. How do we solve this? The basic idea is instead of using an Eulerian point of view in high dimension, we switch to a Lagrangian point of view. What's the Eulerian and Lagrangian point of view? The idea of Eulerian is I fix the observer. So to study the fluid dynamic, I fix the observer at one location and try to get this velocity at any position at time t. But the Lagrangian point of view is I move my observer. My observer is moving following one of the particles in the flow. So if we label the particle with its initial position at 0, Lagrangian point of view is trying to find this function gx, the solution map, that tells you which position of the particle is at time t if it initialized at position 0, x0. And there is a relation between the Eulerian language and Lagrangian language, which says the time derivative of the solution map is actually the velocity. And if your density if every particle follows this v to evolve, then the density distribution at time t is given by this push forward map. So based on this, let's rewrite our optimization of the optimization problem we want to minimize, we want to solve. So the first thing is we substitute this v with partial t of t. And we substitute this rho t with the push forward of g2 at 0. Then by definition of push forward, the first term we can write in this way. So can we directly parameterize a neural network, use a neural network to parameterize this G to solve this minimization problem? The answer is this is not easy to do directly, because here you want the density rho at time t. To get this value, the computation requires the computation of the determinant of a Jacobian of G inverse. So that means to directly solve this, you want your neural network to parameterize the G. You want this G to satisfy invertibility, and you want it Jacobi determinants to be easy to solve at any time t. Then how do we solve this problem? The idea is divide and conquer. If it is not easy to if it is not easy to push G to satisfy all these conditions, how about I divide the time interval into different segments, into a sequence of segments, and if on each of the segments I can push this small g1, small g2 to satisfy the invertibility and the efficient Jacobi determinant computation. Then we compose all this small g1, small g2. We can get we can guarantee that the capital G satisfy the properties we want. So here is what we do. Instead of directly parameterize the solution map G, what we do is we first divide the time domain into time interval into k segments, and let G1, G2 be the small solution map from G0 to G1 and from GK minus 1 to GK. And we impose some structure on this small g, then parameterize them by neural network, so that they are invertible and their Jacobi determinant is easy to compute. Then we write our optimization problem in terms of this small g. The first step is we substitute this partial Tg with a finite difference approximation, and then use summation to approximate this integration over the time domain. And in terms of on the space domain, what we do is we use sampling. Instead of doing the direct integration over the whole space, what we do is we sample particles. We write all these things in terms of the expectation, and then we can sample particles to approximate this expectation. So now we have the neural network, and we have the objective function. We can do in backpropagation, stochastic optimization to solve this problem. This is some numerical results on high dimension solving mean-field games in high dimension. In these experiments, we solve it in 2 dimension, 10 dimension, 50 dimension, and 100 dimension. For all this, the increasing of the dimension does not pose any difficulty or apply our algorithm. And in high dimension, we can achieve a similar accuracy, the similar performance of the result with traditional mesh-based methods. And in 100 dimension, the number of the time for each iteration is not dramatically increased. So we can also using this strategy to do some multi-group and multi-group path planning problems. So as I promised you, I will talk about some connection between mean-field games and normalizing flows. How does this tell us the relation between mean-field games and normalizing flows? So the idea of So essentially, normalizing flow is a generative model. The goal is you give me the data distribution ρ1 and give me the simple distribution ρ0. You want me to find the mapping G that can push my simple distribution as close as to my data distribution. Normalizing flow is also want to find the law of the density to match a simple density to a complicated density. But in practice, people find the normalizing flow is hard to change. You need to change if you want a better result. You need the depth of the neural network to be very high, and this may impose some computational difficulty. And they also observe the chaining of this normalizing flow is very unstable. Our interpretation of this issue is when you chain the neural network, when you chain the normalizing flow, you actually don't impose anything in the trajectory. So your trajectory can be very wild when trying to match ρ0 to ρ1. So our solution is, why not put some regularity on this trajectory? Let's impose our trajectory to be as smooth as possible, as straight as possible. Give me as low dynamic cost as possible. So let's compare mean field gain and normalizing flow. Normalizing flow only cares about the terminal cost. And what we want to say is, let's add some dynamic cost when chaining this normalizing flow. So here is what we propose. We propose to chain the normalizing flow with the KL divergence and in addition with the dynamic cost. And in this way, we can still write the objective function based on G1, G2 until GK. And we chain the normalizing flow with this new objective function. So here is the first result we get. The first row is we directly chain the normalizing flow with the KL divergence. And for the second row, we impose the dynamic cost in the objective and result, and the chain it with the same normalizing flow structure. You can see the second row actually impose the trajectory of the second row is more regular than the first row. And if you compute the Lipschitz bound of each small each row, you will see when we impose the dynamic cost in the objective, we achieve the lowest Lipschitz bound. And this is very so if you, the surprising thing is the non-surprising thing is if you don't impose any regularity on the trajectory, your Lipschitz bound can be very violent. And the surprising thing is if you regularize the objective with the L2 norm of the flow, it still cannot do very nice. It still cannot do a very good job. But if you put the dynamic cost in the trajectory in the objective, you actually achieve a very nice Lipschitz bound of the normalizing flow. And here we compare our algorithm compare with our model with normalizing flow model on the generative task. This is tabular data, and all these methods, they do not have the dynamic cost in their objective. We train two types of normalizing flow. One is real MVP, the other is NSF. We use the same neural network structure, but add the dynamic cost in the objective and we can achieve a similar log likelihood comparing to the methods without adding the OT cost. And we can improve the response of the normalizing flow. So that is all I have for today. To summarize, we propose some numerical methods to solve mean-field games on the low-dimensional space, and with bridge mean-field games and normalizing flow. On the one direction, we can use normalizing flow to solve high-dimensional mean-field games, and on the other direction, we use mean-field game. We use the optimal transport cost to improve the chaining and stability of the normalizing flow. And something that is worth to think in the future is, for example, this is just some example like how to solve the mean-field game on high-dimensional manifolds. And the other thing is this normalizing flow things. You still need to know some density function. For example, you need to pick a very special form of the initial density to learn the data density. And what if we don't have the density function? What if we don't only have the data distribution of the density? Can we still try to solve some things, solve the mean-field game based on these things? And here are the references, and I'm happy to take any questions.
Any questions from the audience or people on Zoom as well? You're welcome to unmute yourselves or add, actually, no, you can't do that, but you can take a question to the chat box.
So in the normalizing flow, so do you know how many steps do you need to get a high quality samples?
You mean the number of flows we?
Yeah, you parameterize, you chop the interval into several pieces. How many samples?
So in our experiment for this synthetic data, tabular data, and for this synthetic data, usually 6 to 10 is good enough. And for image, that's a little bit complicated. For image, we use a special type of normalizing flow, which is called glow. And there are many small steps in that neural network, and that can be a little bit costly.
So you know about this OT flow paper?
Yeah.
So what's the difference between your regularization and that one?
So yeah, that's a good question. So what they do is they know that the velocity is imposed by the value function, is the derivative of the value function. So what they parameterize in their paper is the value function. And what we parameterize in our paper is more like the velocity. It's not directly the velocity, but it's more like we directly parameterize the discrepancy or velocity of the flow.
But you still adding this kinetic energy, so along the flow to regularize your path, right?
Yeah.
Okay, so that's the same. It's just the way you parameterize.
Yeah. And we think that directly parameterized V is better because somehow, according to numerical experiments, neural network is not very, I would not say not very good, but in terms of numerical results, you parameterize phi, the result is not as good as you directly parameterize velocity.
See, but velocity is in high dimension. So if you parameterize that, I think, yeah, I don't know. So it seems harder than parameterize a potential function.
Yeah, but since it's neural network, high dimension is not a problem.
Well, I had a question on the first part of the talk. So you were looking at discretizing the manifold with this 2 or 3 dimensions with finite elements.
I mean, the Euclidean space or the manifold.
Yeah, so here, yeah, around here, yeah, so when you're looking at discretizing the manifold.
Yeah.
So you're right that, if you're looking at finding elements or something, you can do this in 2 or 3 dimensions.
Yeah.
But one way you can discretize a manifold in higher dimensions is with a graph, so you can take random samples from the manifold
Yeah,
and build like the graph Laplacian that converges to the Laplace Beltrami operator and so on. Have you thought about this for the high dimensional setting?
yeah, we thought about this, but didn't follow the direction to do some numerical experiments. One thing is, we haven't find a very good application we can do in high dimension, especially on high dimension on graph. It's usually related to data, but we haven't got a very nice application on why we want to do this. What's the good interaction cost and terminal cost? That's one of the main things we didn't continue to do this on graph. But but our algorithm can still apply to graph as long as you can define this operator on graph.
Any other questions? Any questions on Zoom? Oh, thanks. Okay, well then, we'll thank, Jiajia.
You're what? Yeah, I'm going back. Yeah.